Let's take some time to investigate this phenomenon of hybridization a little more closely. If we remember something like, let's just use CH4 for our example, carbon has that 1s2, 2s2, and 2p2 orbital. When it hybridizes, one of the electrons in the 2s is going to go into the p orbital, and then the p orbitals and the s orbitals are going to merge together. And I found this nice little diagram here that helps visualize that. So as carbon hybridizes, it's going to put one electron here, one electron here, one electron here, and one electron here. And then these orbitals all kind of move around each other so that they're not overlapping. They don't want to take up any of the same space, and we end up with this shape right here, this tetrahedral shape with carbon being in the middle. These are its electrons on the outside. And then I could see a hydrogen bonding to each one of these. And hydrogen would have its own s orbital. It's overlapping this. And so that's how these orbitals are really merging together and hybridizing. They're just trying to find a way to take up some amount of space without overlapping each other and being as far away from each other as possible. If we look at an example of 3 domains, so this would be 3 domains. Well, then we see that one of my s orbitals merges with 2 of my p orbitals. And so we only get 3 merged orbitals. And we would have another p orbital that would be above and below this. That would just be hanging out, not doing anything special. If I look at my 2p hybridization, well, then this is going to have 1s, 1p merging together. And it's going to sit on one side of that atom. And in something like carbon dioxide, this is really useful to look at because I've got this carbon. I'm going to have this p orbital. Let's try and draw that here. Let's try and draw that. Use 2 different colors. It's going to look like this. Another one on the other side. Okay. And then I would have 2 oxygen atoms over here. And those will each have an orbital that's overlapping with that. So that's where that single bond is going to come from, but CO2 has a double bond, right? It's got that carbon double bond to that oxygen. Well, the reason this is a single bond is because this is taking up 3-dimensional space. If we look at these diagrams up here, this is taking up 3-dimensional space, and so there's not room for a second bond over the top of this. And so this carbon still has, and it's used one of its electrons in the s orbital and another electron in the s orbital, merging with the 2 empty p orbitals that it's got, and it's going to leave 2 of its p orbitals intact. So let's show this in green. And so it's going to have those intact up here. And likewise, these oxygens both have those orbitals that are empty. And so to form a double bond, these orbitals are going to merge together. And so we end up with this space above and below the atoms where there are electrons flowing around. And so we've got the single bond right here with 2 electrons in it. And then we've got our double bond above and below this atom. Okay, so this is one double bond. The other double bond would have to be in front of this, so I would have to draw it more like this, right? Because this is still 3-dimensional space, and we don't want this p orbital and this p orbital to overlap. So this one would be in front of and behind this carbon and oxygen. And so we can imagine a triple bond. If I had a triple bond, let's just imagine for a second I've got 2 carbons here. They're triple bonded with each other. So I've got my single bond here, and then over the top of these, both of these carbons are going to have that double bond. Okay, so this would be my double bond, above and below. And then my triple bond is going to be in front of this. And so it's going to be taking up this space in front of it. And so this whole thing, it gets pretty messy. gets pretty crowded in here. We can see how these three bonds, all three bonds, are really going to make this hard for this carbon to move around. Where if I just had something like a single bond up here, if I just had this bond could kind of spin and move around. But these bonds down here, this double and triple bond, it really locks them in place. It causes a lot of rigidity. And on a macro scale, we could think of something like a plastic. A hard plastic is going to have a bunch of triple bonds in it to help it stay solid. That should help us get a better comprehension of how these bonds hybridize and what that really means and looks like. You don't need to be able to draw these models, but you should have an idea that they are there. You should be able to, if you see this, if you see something like this, you should be able to identify which type of hybridization it's participating in, SP, SP2, or SP3.